June. He received his Doctor of Science degree from University of Tokyo, Finland in 2012. He's currently working in Computer Systems Laboratory, University of Tokyo, and the Tokyo Center of Computer Science as a researcher. His research interests include software system support for neuron-chip platforms, system-level 3D microprocessor architecture design, and software engineering.
Sorry, where is the screen?
Anyone help him?
This seems to be maybe Control F.
Control F or
L?
Control L.
Sorry, don't understand. Okay, thank you very much. Okay, so I'm from Finland. My name is Thomas. So I came here like 2 days ago from Helsinki to London to Vancouver here, and I think the weather here is really nice. I mean, it's really nice. It's plus 10 degrees, you know, a little bit rain, but in Finland nowadays it's minus 15 degrees and snow. So I think
you should go further south.
So it's 25 Celsius of temperature difference. I think it's really nice here. Yeah. Yeah. Talking about the difference for weather, there's another difference. I remember that Nokia mobile CEO in 1984. Of course, Nokia is not very good nowadays, you know, because of the new CEO. But back to that time, Nieminen, that name is, he said that when some startup in Silicon Valley opens his garage, he faces like 50% of the world market. When a startup in Finland opens his garage, he faces like 1 meter of snow. I think here, when someone opens his garage, he faces this rainy and cloudy weather. But yeah, anyways, I'm from that country. Yeah. So I'm here to introduce our latest result, research for high efficiency, low cost, heterogeneous 3D network on chip design. So this session is totally on this kind of 3D design. So we are pretty the same in this topic. And we already know that future chip multiprocessor will be highly probably on network on chip architectures, and these 3D-dimensional and the 3 silicon wire things will be likely to be the next step of our chip multiprocessors. But many previous researches are focused on these kind of symmetric, homogeneous, or fully connected architectures, while in our research we focus on this asymmetric, we focus on this heterogeneous and partially connected architecture. So based on this, we propose 2 heterogeneous designs, one for efficiency and the other one is for performance. So as I think almost all of you already know, a lot of for this background for network on chip, so I'm going to pretty fast for that. It's based on this system on chip, and because of the complexity and bottleneck for this bus system, so network on chip was proposed. It's already over 10 years, so it's not a new system, but of course there are a lot of things to research. And this is typical network on chip architecture. We have processing units, network interfaces, and those routers and those links. There are a lot of tiers and nodes to this kind of mesh architecture. And we already have some products. Some are in laboratory, some are in the market. For example, these Intel things, and they have even constructed the x86 instructions chip. And the Telera tile family is available for your purchase. You can buy it like $400, something like that, for one chip. I don't know how many of you already own this chip. Not very much, right? So still lacking, I think, still lacking some market. Of course, the next step is for 3D. It's just like our buildings. Like several hundred years ago or 1,000 years ago, we rely on these flat buildings. But when the population rises, we have to rely on these multi-layer or multi-level buildings, like this building. We have those. How many levels do we have in this building? Fair amount. I'm not living here; it's too expensive. 20 or 30 floors? No.
15. 15.
15. Okay.
15.
15. Okay, 15. But I think there are a lot of high-level buildings in Asia, Asian countries, like 100. Why? Because we are constrained for space, right? So that's pretty simple. When we are constrained for space, we go 3D. And we are faster, because if you're going to spread those rooms in 2D, that's too much space. And for 3D, we have to connect those layers. You already know we use these TSVs. It's just like the elevators here. So those TSVs are placed on between layers to provide this vertical connection. So this shows pretty similar as the previous papers. We have 2 layers here as shown, and 1 layer is for processors and the other layer for caches, and those we have 16 nodes or tiles, and they are fully connected by those TSVs or pillars, if we change another word. Of course, we are talking about floor connection. So it's something like here, we have floor connection between layers, between these floors. I don't think so, because we have constraints. How many elevators do we have in this building? 6, right? 6. Okay, we have 6 elevators. Why? Well, because we have so many rooms. Why can't we have like 100 elevators? It is possible. Is it possible? Yes. I think yes, but why? Because of constraints for the cost, right? We don't need that much elevator. Of course we can, but we don't need that much because of manufacturing cost and the utilization, something like that. So we only need 6. In some other buildings, we may have only 2 or 3 or 4. So that's the problem. We want to limit the number of TSVs because of the cost. And furthermore, in other cases, we have to try to improve the placement for the TSVs to achieve an optimal placement. So that's the reason, because it's expensive, and of course maximum performance can be gained by this floor connection, but because of cost. So we have to optimize for the number and the placement for the TSV, so we can achieve an optimal number and placement for TSVs. And here shows one possibility, which is an optimal placement for TSVs in an 8x8 mesh. So if we think about a smaller mesh, like we can divide these 8x8 by 4x4, right? We have 4 meshes, it's the same. So we have those gray nodes are those nodes with TSV. So as you can see, we have only 1/4 of the TSVs. So 16 nodes, we have only 4 TSVs. So for totally 64 nodes, we have 16 TSVs, right? Those are, you know, elevators. So why do we place for that? Because this is one kind of optimal placement. If you place those TSVs in this kind, we can achieve maximum 1 hop access for any node to the next layer. So no matter which node you are, you can go to the nearest TSV in maximum 1 hop. So this is kind of, how to say, minimum number of TSVs required for this kind of 1 hop access. So you need 16 in 64. And of course, the routing will be changed it can't be nearest or something like that. It's just a modified deterministic routing to the nearest pillar or TSV, so we can reach the nearest TSV in one hop. So as you can see, all the nodes can reach the nearest TSV for just one hop in this optimized design. Okay, so here is about the 3D TSV, and in fact it's based on our previous research. So in this research, we start from this kind of application traffic. So the previous paper showed that they use something like uniform traffic, or what's here?
Just use the X.
Okay. For example, uniform random or transpose or something like that to analyze the performance of the on-chip networks. But for our experimentation, we use this real application traffic because we think it's more realistic. Anyways, you have to make those final chips based on cores and caches. And in this case, you have a lot of messages, including control messages and date messages. You have these cache coherence messages. So it's not just like a uniform random message. Uniform random, of course, every place is random. It's like the street. We can, of course, assume that every street has the same amount of traffic, but it's not realistic in practice, right? We have some places in the city center that is a hot spot. That's very natural. So in this case, we are trying to play more with the realistic traffic. So in this case, we categorize our on-chip message in several types. First is the control message, which contains those cache requests, response, forward, invalidate, for example. Most of them just 64 bits or 8 bytes, for example. And of course, those date messages. These messages contains a full cache line and, of course, the control header. For example, if we assume cache line 64 bytes, then these data messages are 72 bytes. So that's the two different messages. And of course, modern NOCs are designed to be like 128 or 256 bit of the fleet size. So if we think about 128 bit size of the fleet, then the control fleet can be transmitted within one fleet. And the data messages can be transmitted in 5 fleets. So that's the case of the real application, if we think about that. So based on these architectures, we conduct an experiment, and the results show that we use this Splash testing suite. I think many of you have heard about that. If not, check the references. Those programs, on average, they have 79% of the data messages. So it's very high value here. Specifically, we focus on this FFT to gain more details for one application. From here, we have 22 million of executed cycles and generated about 2 million messages. And of these messages, 77.9 are control messages. And if we think about the equivalent number of transmitted fleets, we think the data are 5 fleets. So it's totally 4.1 million of the fleets. So 2.1 million of messages, 4.1 million of fleets. And furthermore, this 93% of the control and 62% of the data are interlayer, which means they are transmitted between layers. We think about this figure. So we have one layer of processor and another layer of cache. So those transmitted between layers are interlayer traffic. And of course, most are interlayer traffic. So that's pretty big number of traffic for data and control. So to summarize, to conclude, we have these findings that control messages dominate the network in terms of number of messages, but data messages dominate the network in terms of total number of leads. And most of the messages are transmitted between layers. That's what comes from the real application traffic. So if we think about some transpose or uniform random, of course we can't get this value, but from the real application, that's the result. Based on these discoveries, our method will compare directly from another paper. This paper, a case for heterogeneous on-chip interconnect from CMPs from Mishra, I think is from PSU. It's in ISCA 2011. In his paper, he proposed this kind of heterogeneous design. And in this kind of design, like a cross or X or something like that, and he proposed these wide links between those big routers, those dark ones, and those smaller routers and narrow links. So they propose that this architecture is the best, and they compared with several others. However, in our paper, we found that we can improve their design far more in terms of efficiency or performance. Okay, so this is our design. We have the same number of routers, but we have fewer number of wide links. And the routers and link design are a little bit different from them, but of course we are based on them. So we have the same two types of routers: the big routers, which is large and high performance, and the smaller routers, which is focused on efficiency. And in our approach, we have 16 big routers and 48 smaller routers, as shown here. Those connected with layers are big routers. And we, of course, have two different types of links. And in this paper, ISCA 2011, they used 56 wide links. In our paper, it's only 48. So it's 8 less wide links. So we next analyzed the different types of links. So we decide we have to use different kind of lead width. The standard design for homogeneous network is 128 bits. We use two designs. One is 72, 144. This is for narrow and wide links. And the other design is 69 plus 192. So we have two designs. Of course, they have different values for transmitting data in 8 fleets or 4 fleets or in 6 or 3. And the total width of the fleets are shown here in terms of number of bits. So based on these two designs, we analyzed the total link width, the link area, and the power consumption, these values, for the homogeneous design, the two heterogeneous designs. So those numbers I'm not going to read out, but you can compare with them. And of course, if we have those links, we have those routers as well, big routers and smaller routers. The original homogeneous routers, 128 bits of fleet width, is 0.47 square millimeters of area and about 1 watt of power. So we have that much total area and total power for 64 routers. And for two heterogeneous design, the power and total area are shown here as well. It's reduced significantly for this 72 and 144. So based on the aforementioned design for these kind of things, we compared our design with their design. So the experiment is based on GEM CIMIC simulation environment. We have 3D CMP with 2 layers, 1 layer of core and the other layer of cache. So we're running the network with 3 GHz and the core 2 GHz. We use Solaris 9 and the cache coherence protocol here, and we use Splash 2 Spectre BBT PCH for our benchmark. So here is the result. Basically, we show 4 designs compare. This one, heterogeneous diagonal, is by ISCA 2011. So it's their design. As you see here, heterodiagonal is the design shown here. So they call it diagonal. So it's like an X, but it doesn't matter. And we have 3 of our other designs. One is homogeneous, which means it's the same here, but all the routers and links are the same. So it's a homogeneous design. And we have 2 heterogeneous designs. One is 72, 144, and the other is 96 and 192. So we compare these 4 designs in terms of first execution time of applications. As we can see, our heterogeneous design reduces the execution time significantly. We can see it's about 10 to 20% compared with the homogeneous design. And if we think about this heterogeneous diagonal design, it's much worse even. So what's the main reason behind here is about the placement for these kind of routers or TSVs. It's very important because their assumption is based on uniform random traffic and transpose traffic. That's the design. That's the design thoughts from them. But as I said, the real traffic from applications will not be uniform random, will not be transformed. So it will be, you can't predict, in fact. So you can't just put those routers in center of the network and expect some good values. In fact, if you think about these 39 or 31, if they have to access the next layer, they have to go for 3 hops to access. And there are a lot of routers, they have to use extra hops to access the next layer. So that's the problem for this design. But in our design, every router can reach the next layer within 1 hop. So that's the main reason for the problem of their design. And with the optimized design, of course, we achieve better execution time compared with homogeneous design. And that's one case about the execution time, and the other one is about the energy delay product. In here, we can see that the gap between wider even. And for 72, 144 achieved better than this 96, 192. It's the best in this case. So in another word, that if we want to achieve better energy efficiency, this 72 design is the best. If we want to achieve better performance, this 96 is best. But if you want to keep like a balance, I still think this 92 is best. So because it achieves better performance with a little bit sacrifice on this energy delay product. So it's still of course, they are all much better than the other two designs. So we propose two heterogeneous designs which are much better than previous designs. So to conclude, of course, we propose the design based on network on chip and 3D TSV integration. And because of the manufacturing cost for the limitation for 3D TSV, and so we propose heterogeneous, asymmetric, partially connected 3D network on chip. And our experiments show that compared with the homogeneous design, average execution time are reduced by 5% and 20%. And compared with the heterogeneous design with diagonal placement, our average net energy delay product can improve like twice as better than them. So it shows the advantages for our design. Okay, thank you very much.
Questions?
Sorry, in your simulation, have you simulated the TSV?
Yes, of course.
And you remember more or less which is the injection rate of the TSV?
Yeah.
Which is more or less?
Injection rate.
Okay, the data rates of TSV.
Yeah.
Which is?
You mean for each TSV, the data rate?
Yes,
TSV?
for each TSV.
Yeah, we didn't include in this paper, but we include in another paper.
But more or less, it could be 10 gigabit per second or
Yeah.
5 gigabit per second, more or less.
Yeah.
All right.
But it depends on the configuration of the system. Yes, we.
And also depends on the number of TSV you want to embed in your
Yeah.
system.
Yeah, of course. Of course, we just think about the elevator. It's the same. I mean,
Yeah, exactly.
Yeah, of course.
All right, thank you.
Okay. I think one of the problems that not just you, I guess the whole community has is that we don't know what is optimal,
Yeah.
right?
Yeah.
Next year somebody will do better
Yeah.
at a different cost. So
Yeah, of course.
It
So
would be really nice to know what is the optimum, the theoretical optimum, how close are we?
Yeah, of course. So in this paper, we didn't use this word optimal in our title. So no optimal, right? High efficiency, low cost, not optimal here. But in fact, this kind of placement, why we say it's optimal? Because it's verified by our partner in University of Stuttgart. They use like a mathematical tool, CPLEX, by IBM iLog CPLEX. It's like IRP. So this is the result from the IRP. So in terms of average hop count for the whole network, it is the lowest. So in terms of this, it is lowest. That's the result from the IRP.
Well, for a given cost, but I can do it.
Yeah, if you if you have
better.
other constraints, of course it won't be. Yeah, of course. But I mean, for the average hop count for the whole network, it's the lowest. Yes.
I mean, this looks pretty random. You keep saying like one hop. If you just use one hop as a simplistic criteria, wouldn't just one every 9? You just need one fat tap every 9.
Sorry.
Process, right? I mean, well, I mean, if you're just talking about one hop, wouldn't you have one every 6? Oh, you can have the diagonal. Sorry.
Yeah, I mean,
why you not be able to connect diagonal?
It's not like random. I mean, it's the if you split those into 4.
Splitting and
Splitting. So that's the one you are replicating.
Exactly.
You are replicating, right? So
and
this is
you
4 by
can
4. Yes.
Split and you've got in every 4
Yes.
corners.
It's like divide and conquer method.
If you make the 100 or one,
Yeah.
16 by 16, you have the same pattern.
Yes, that's true. Yeah, and to get those minimal or optimal solutions, we have collaborate paper for University of Stuttgart. We use another optimization solution from IBM iLog CPLEX. So for IRP solutions, yes. This is just one result from our another paper. Yes.
I don't need to discuss this idea with you. You consider this design optimal because every core will take one hop to reach to the vertical TSV.
Yes.
I think if we know the traffic pattern,
Yeah.
we will know which core will need to communicate vertically.
Yeah.
Because not all the core will communicate vertically.
Yeah.
So if you based your design on knowing the traffic,
Yeah.
you will position the TSV in better position for
Yeah.
performance.
Yeah, of course, of course.
I think so.
Yeah, yeah, that's true. I totally agree with you. But the problem is that we can't know this traffic beforehand. That's the main problem. Because the application, different applications have their different role. For example, running on your PC or on your notebook, you can't tell what application you will run. You may run a game or some music player or video player or some browser. You don't know.
For application-specific NOCs, if
Yeah.
you know the application.
Yeah, of course, I agree with you. That's true. But in our design, we consider general purpose NOC. Yes.
Oh, cool. Can you go back to slide 9?
Yeah.
Slide 9?
Slide 9.
Oh, I guess it's kind of
Okay, this one. Yeah.
So is it actually possible to have diagonal connections between the areas?
Sorry.
Is it actually possible to have diagonal connections like between the hops, like hop diagonally instead? Like would that change anything?
Diagonally? Sorry.
Like say jump from 56 to 49, like have a connection between those two.
56 to
49.
49. So these two?
If there was a possibility.
Is it?
What did you mean? I didn't get it.
Diagonal.
We can hook it directly, connect those diagonal dies.
So you mean connect these two dies?
Yeah.
Yeah, yeah, it's possible, but that's not mesh, right? Yeah, we're talking about mesh.
Okay.
Yes, yeah. So in this paper, we assume mesh connection. Yes.
All right, so we thank all the three speakers for very interesting talk.